Here we are now in 2 dimensions. In a 1D world, it's really easy to specify the position of something. You just need to use one number. Define a reference point, and then say your position is 7.2 meters, and we know you're located right there. Or your position is negative 12 meters, and we know you're located right there. That one number is sufficient to place you at an exact spot in the world. And a quantity like that, where you just need one number to specify it, we call a scalar. Scalar is a term for some quantity that you just need one number to fully determine. But in 2D, it's a little more complicated because you can't just give one number to say where something is. So if I have an x-axis and a y-axis here, so horizontal and vertical, and I want to say where something's located, if I just said, well, there's a reference point, it's at 12 meters. Well, you know, is that 12 meters off in this direction, or 12 meters that way, or 12 meters that way? You need more information. You guys know that we usually use an xy coordinate pair. So we say how far the object is located in the x direction, its x coordinate, and how far it is in the y direction. We need those two numbers to specify some specific location. Now, a number like that, a quantity like that we require two numbers to specify, we call a vector. So a scalar is something where you need one number to specify it. A vector is something you need two numbers to specify. And we usually represent it on a diagram as an arrow. So here in 2D, we can represent the position of our object using this arrow. And I'm going to call that arrow R with a little harpoon above it. That harpoon is like the arrow itself. That harpoon tells us that this quantity is a vector. It's a quantity that requires two different numbers to specify. And we use the letter R to specify a position in 2D because we can imagine that we have a circle centered at the origin and we are located on that circle. And so that position vector, that arrow, is like a radius of the circle, hence the letter R. So we say our position in 2D is represented by a position vector, a little vector symbol right there, and it requires two different numbers. 8 meters is your x coordinate, 4.5 meters is your y coordinate. We call those two numbers the components of the vector, the components of our position vector. It has two of them. Okay, so let's recap here, scalars versus vectors. A scalar, that's a quantity represented by just one number. Whenever we're in 1D, everything is a scalar. You only need one number to specify it. And a scalar has no direction to it. A vector, on the other hand, always requires two numbers to define it. And we often draw it as an arrow. So when we're in 2 dimensions, many of our quantities are now vectors. Not all of them, but many of them will be vectors. They will require two numbers to specify. And I say vector here is bold because when you see in print a quantity that has a little arrow over it or a harpoon over it, that is a way of indicating notation-wise a vector. Or even without an arrow or a harpoon, a quantity that's just bolded is a vector. So any of these in print would represent vectors. It's bolded, so you know it's a vector. If it's not bolded, like this A, that would be a variable representing a scalar. Let's look now at displacements in 2 dimensions. Here we have another map, x direction, y direction, a starting position, and an initial position, and some path we travel along to get from our point A to point B. Now, in 1D, it's really easy to specify a displacement also, because you could say, if you start at 7.2, my delta x is plus 5 meters, and you know you're going to end up right here. Or my delta x is minus 5 meters, and you know you're going to end up right there. With just one number, we can specify your change in position. But now here, if I said, oh, my change in position is 5 meters, well, we don't know if that's 5 meters this way, or that way. we need more information. We need two pieces of information. Thus we know our displacement is going to be a vector as well, because it'll need two numbers to specify it. We can indicate it by drawing an arrow from our starting position to our ending position. That represents the change in position. Change, delta, in position, r, with a vector symbol over it. This is displacement in 2D, delta r. And it has these two different parts to it. I can make that arrow sort of like the hypotenuse of a right triangle. And the sides of that triangle represent my change in x position and my change in y position. Delta x here is our final x-coordinate minus initial x-coordinate, 5 minus 2 meters. And my delta y here is our final y-coordinate minus the initial y-coordinate, 1 minus 5 meters. I need these two values, the delta x and the delta y, to say my displacement. So between these two events, my change in position requires a change in x of 3 meters. I moved 3 meters this way in the positive x direction, and a change in y of negative 4 meters. Negative 4 meters in the y direction. These are now the components of my displacement vector. Notice the components can be negative. If my change in position is in the negative direction, that's a negative displacement. It's often useful to also know the length of this straight line path from beginning to end. So if I want to know this length, we have a term for it. We call it the magnitude of the vector. It's like the length of the arrow. Notation is like this. If A represents our vector, the little vector symbol over it, then if I put absolute value signs around the A, then that means the magnitude of A, or the length of the arrow. So here's our A vector, here's our x component of it, here's our y component of it, like the legs of the triangle, and the length of the hypotenuse here, the length of the arrow, absolute value of A, that's what we call the magnitude of A. And it's always going to be a positive number. And we've got right triangle here, so we know that we can use the old Pythagorean theorem to find the magnitude. If we know the legs, Pythagorean theorem, a squared plus b squared is c squared. So to find the magnitude of our displacement, we take our delta x squared plus our delta y squared, add them, square root, and find our magnitude of the displacement. That's going to always be a positive number. So it's 5 meters directly from here to here. That was our displacement. If we had returned all the way back to where we started instead, then our displacement would be 0. We would have traveled a long way, but if we returned to where we started, our displacement would be 0. However, our distance traveled would not be 0. The distance traveled, also called the path length, the length of your path when we're in 2D, we can represent by a lowercase d. That's always a positive number, and that'll be a change in reading on an odometer, like how far you walked. So in this diagram, we could find our distance traveled, our path length, by measuring this whole distance here, counting off your steps, or wearing a pedometer, or looking at the change in your odometer. That is d, your distance traveled. It can be quite long, longer than our displacement. In general, the distance traveled has to be greater than or equal to the magnitude of your displacement. The shortest path from A to B is going in a straight line. So if you move in a straight line, your distance traveled is the same as the displacement. But if you don't move in a straight line, your distance traveled will be greater than the displacement. Okay, I've got some exercises for you to try out. Here are a few, let's say 8 different displacement vectors. So again, x and y directions, and each time we have a starting position and an ending position, a starting position and ending position, and I've drawn in the displacement vector that connects those two, and given the displacement vectors different names. So my questions are, of these 8 different displacement vectors, which ones have the same magnitude but different direction? Which ones have the same direction but different magnitudes? And which are equal? To be equal, two displacement vectors have to have the same magnitude and the same direction. Okay, pause the video, answer those questions. Ready? Here are the results. Watch that movie.